let's look at what we can do with these thermochemical equations. One of the most useful things that you can do is predict how much energy is going to be absorbed or released by a chemical reaction that is very difficult to do in the lab. For example, let's take the formation equation for water that we were looking at a little bit ago. Now, this is a fairly easy equation to measure in real life. All you have to do is a calorimetry experiment where you've got a reaction vessel where hydrogen and oxygen are reacting with each other to make the water. And you can see how much heat that releases per mole of hydrogen or per mole of water that forms. But this is a very difficult reaction to do. Not very difficult. You can do it with an electric current. You can pass a strong electric current through water and get this to happen. In fact, this is, you've got a cheap source of electric power like a nuclear reactor on a submarine. This would be a way that you could make fuel hydrogen for your fuel cells and also some oxygen to breathe in the submarine. You can convert water into hydrogen and oxygen. How much energy is it going to take to rip up that water molecule so that you get an H2 molecule and half of an O2? Can you guess? Now what I did was I took this reaction and flipped it. So whatever I do to the chemical side of the thermochemical equation, I also have to do to the thermal side. In other words, the delta H gets flipped as well. And to flip it, you flip the sign on it. So flipping a reaction over simply flips the sign on the delta H over. Now what happens if you write down that same equation like this? Because it is the same equation. Suppose I multiply through by 2 in order to get rid of that half. What would delta H be now? Can you guess? It's not going to be the same as what it was up here. This is like a combustion reaction as well as a formation reaction because this is a fuel material. And if you double the amount of fuel you've got, you're going to double the amount of product you're going to get, but you're also going to double the amount of heat that you get. So delta H for this reaction, since I multiplied this part by 2, delta H for this part ought to be 2 times 285.9. So what's that? It's like minus that, I think. Is that right? Yeah, if I have this written wrong. This should be 285.9. Then I have everything consistent. Okay. So, reactions can be scaled. Thermochemical equations can be scaled. And that's what we were doing here. We scaled this up by a factor of 2, so you also have to scale up your delta H by a factor of 2. Okay? So these are things that you can do with thermochemical equations. Another thing that you can do is add them. So for example, if you've got CO gas plus 1/2 O2 gas going to CO2 gas, and delta H for that is minus 283.0 kilojoules. And let's suppose you have, how about that's, let me see, let me look it up. It'll be minus the formation for CO2 gas. So it'll be 393.5 kilojoules. So suppose I have these two reactions, and I want to add them up. So the carbon monoxide burns to make carbon dioxide, and then the carbon dioxide falls apart to make carbon and oxygen. Well, that won't happen in real life. Combustion reactions don't run it backwards. Imagine if you had a log and you burn it in a fireplace. You get the smoke and the ashes and the heat. The ashes and the carbon dioxide that the combustion makes don't come back together to make the log. So this just doesn't happen in real life. But we can make it happen on paper here. So if I add this reaction to this reaction, what am I going to get? Well, let's add the chemical parts. There's a CO2 on the right and a CO2 on the left. So they're going to cancel out. So all that's going to be left when I add these together is CO gas plus 1/2 O2 gas goes to, and on the other side, carbon solid plus O2 gas. Now notice that I've got O2 on both sides here. If I subtract 1/2 O2 from each side to get rid of it, or if I look at it this way, half of this O2 will cancel out half of that O2. I'm going to get, that's an S, I'm going to get this. And what's delta H for that reaction? It's going to be this plus this. So if you add those two things together, you want to get what this is going to be. So what's that? This is going to be 393.5 minus 283. So that's like what? Like 110.5. So you add this to this and you should get that. All right. So you can, to recap, you can flip reactions over. If you flip the chemical part, you're going to flip the thermal part. You're going to flip the sign on this. You can scale reactions up and down. Scaling means multiplying through by a constant. If you multiply this whole side by a constant, like 2, you'll have to multiply this by the same constant. And finally, you can add thermochemical equations together. Things that are on the right side of one will cancel out with things that are the same on the left side of another. And then you write down just all of the things that haven't canceled. And when you add equations, thermochemical equations, you're also going to add their delta H's to get the final delta H. Now these are all the small pieces of the problems that we're going to be doing on this worksheet. You're going to need to be able to write out formation equations. You're going to be able to write out combustion equations. You need to be able to flip equations, scale equations, and add equations. And then you're ready for the rest of the worksheet.